Hi. My name's Bobby. I'm here from Bristol. So I'm going to talk about something quite similar, looking at post-processing rainfall forecasts, particularly in East Africa. So this is work that I've been doing mainly with Peter Watson in Bristol and Lawrence Aitchison, but we've also been working with the group in Oxford, which is Andrew McRae, Fenwick Cooper, and Tim Palmer, and also working with Dave McLeod and John Marsham, who are kind of experts in African meteorology. So I'll just give you a bit of an introduction to why we're interested in this problem. So this is what some people might call equatorial East Africa. It's quite a it's got quite a lot of stuff going on, a lot of diverse areas. Some of you may know that it is currently going through one of the worst droughts in 40 years. There's a lot of drought going on, but also that it's prone to flash flooding. So extreme rainfall that tends to, there's been already this year, there's been significant flooding in Somalia, Ethiopia, and Uganda. It's quite a heterogeneous area, domain. So it's kind of, you've got Lake Victoria, huge inland water body. You've got mountains. You've got the coasts. You've got different rainfall seasons. So they have long rains and short rains. The long rains in March, April, May, and the short rains October to November. October, November, December. Also, I guess what's interesting about this region compared to maybe other regions which people typically study with rainfall is it's dominated by convective rainfall, much more so than other regions. So it's a bit of an interesting area to look at in terms of forecasting. And because there's so much convective rainfall, it means that a lot of the kind of conventional forecasts, which have convective parameterizations, tend to perform poorly, particularly capturing the diurnal cycle and rainfall intensity. So our aims are to look into this and see if we can use some machine learning techniques to improve on these forecasts. Particularly interested if these models will allow us to better forecast extreme rainfall in order to better improve early warning systems in the region. And we're interested in how well machine learning models are going to deal with convective rainfall. And as an output, we've been providing input. There's a World Food Programme and Oxford and Google joint workshop trying to look into how methods like these might improve seasonal forecasts, but also early warning systems and things like that. So the observations we're using is what's called iMerge or iMerg. I don't know if you pronounce that. So these are satellite observations. They're infrared and microwave combined and calibrated against rain gauges. It's actually half hourly, but we're using hourly, and it's at 0.1 degrees resolution. And the reason we're using this is it tends to be one of the highest quality, highest resolution sources of observations in this region because not so many rain gauges to look at. And the forecast we're taking in is the ECMWF IFS HRES, which tends to be one of the best performing in this region. Also looking at hourly, regridded to 0.1 degrees resolution, and we're using 20 input forecast variables, including things like obviously rainfall, but things like convective available potential energy, convective precipitation, humidity, and temperatures, and things like that. So currently we're training on a 2-year window. We're training on a region which has a kind of consistent IFS model. And so that's 2-year window. We're currently validating on June 2018 to June 2019. You might notice there's a bit of a gap there, and that's because we're deliberately holding out the 2018 long rains because they were particularly extreme rainfall. So we want to save that as an extreme holdout test set. And the modeling approach we're using, so as I mentioned, we've been working with Tim Palmer's group, and they have previously used conditional Wasserstein GANs to downscale precipitation in the UK at 6 to 18 hour lead time. That's the same lead time we're doing. So yeah, as I said before, we're taking in some forecast variables. We're also taking in land sea mask and the orography, things that we think will be important. Yeah. So I think probably a lot of people will know what a generative model is already. I'll just keep talking about it because it's in my slides. But you're obviously, I'm sure lots of you are familiar with ChatGPT and DALL-E and all these other things that are in the news, generating funny looking things. So yeah, there's been a lot of work done it's particularly in image generation using GAN. So there's, some really impressive things you can do with a GAN, like this one I like, where you can specify, tell it where to draw things and what to draw, and it'll roughly draw something with things in the right place. And you're going to kind of see where this is going. Like we can tell it if we give it like the rainfall, a picture of like what the rainfall forecast was, it can kind of maybe generate something more realistic. But I guess one of the key things about a generative model rather than just a kind of deterministic model is that we obviously want to generate ensembles cheaply, so which allows us to quantify risk. So it's very important that we have a generative model. So yeah, as I said, when we're using GAN, generative adversarial network, it's very well used in image generation. And as Sebastian said, it's an implicit model in that it learns a way to sample from the probability distribution of image based on the input in this case being the original forecast and the land sea mask and the orography. And I guess one way to think about these things is that rather than having a traditional model where you've got a model that learns against a loss function, you kind of replace that loss function with a discriminator as well, which is kind of acting as a distance measure between the probability distribution that you're generating and the actual probability distribution. So yeah, and yeah, as I mentioned before, for those who are interested, we're using a Wasserstein GAN, which tends to improve the stability of training a GAN. We're also adding, based on Andrew and Tim's work, an extra term in the GAN, an extra part of the loss function, which kind of constrains things to be close to the ensemble mean. This is actually something that was, I think, originally based on one of the DeepMind GAN papers. They also use this as a kind of regularization term, just to kind of constrain the output to be near the ensemble mean. Oh yeah, this is just a kind of like a little cartoon of how these things work. So the generator produces something really bad, and here's the real data. And the discriminator learns very quickly to tell that that's bad. And then it generates something else, which is a bit better. The discriminator learns very quickly to still tell that's bad. And then eventually maybe the generator gets good enough at generating things that the discriminator can't really tell what's real and what's fake. So it kind of manages to trick the discriminator, and they kind of play off each other like this. And just to kind of demonstrate generative models, these are actually images generated by DALL-E here. This is what DALL-E thinks a cartoon drawing of rainfall is, and this is what DALL-E thinks a realistic weather forecast of the UK looks like. So, yeah, so just presenting some results that we've got at the moment. So we're looking at, so first of all, look at some kind of more climatological measures. So we're looking on the left here, we have radially average paraspectral density. So this is just a measure of like how realistic does our forecast look? Is it kind of producing the right kind of frequencies? So the GAN is there in blue. You can see that it improves a decent amount. So the red solid line is the raw IFS, but obviously we don't expect the IFS to line up with the iMerge observations because that's not what it's designed to do. So we have to apply a good baseline to the IFS. So what we're doing is we apply quantile mapping. We apply a particular kind of quantile mapping to deal with the data we have, just using neighborhoods of regions to calculate the quantiles. So you can see the dashed red line there is the forecast, including quantile mapping, just as a good baseline. So yeah, the GAN tends to produce realistic looking images. It tends to produce, correct the paraspectral density by a decent amount. On the right here, we have a quantile plot. So you can see that, I don't know if you can see all of them because they're a bit small, but you can see how the GAN, the blue crosses are kind of lining up quite nicely with the line, except until you get to very high quantiles, about 99.999th percentile, sorry, starts to diverge quite a lot. So we have quite heavy tails producing quite extreme rainfall, like a bit too much, a bit over predicting. Whereas the IFS, as mentioned before, tends to underpredict at the extremes, which yeah. And then the green there is the quantile map one, which is also doing a decent job. I guess one thing that's interesting about this model, which is kind of even a quantile map, a good baseline like quantile mapping can't really do, is improve the diurnal cycle. So this is a plot of the hour of peak rainfall in East African time. So typically, what the IFS does is it kind of tends to predict rainfall in midday quite a lot, and it doesn't really do it in the afternoon. So you can see iMerge, there's a lot of red, IFS, a lot of beige, and the GAN's kind of correcting a lot of that quite nicely. Yeah, so, you know, it's obviously, it's still not perfect, but it's still capturing some of the, it's still managing to improve diurnal cycle overall. And yeah, this is just another kind of different look at the diurnal cycle, I suppose. So if you look at the whole domain on the left here, you can see how the red one, IFS, tends to peak at midday. It's kind of well known that I think it tends to peak at midday. And you can see how the GAN is aligning a lot better with the observations, the kind of where the average rainfall is. And this is something that is consistent if you look at different percentiles of rainfall, not just the average, you know, looking at medians or high percentiles. I also included, yeah, I guess what I hadn't given you as background is that a lot of people have been looking at convective permitting models in this region as well, because obviously that's one way we can try and improve forecasts. And these do a better job at, you know, these tend to correct the diurnal cycle pretty well, but they still do struggle in regions like Lake Victoria. They don't quite get it perfectly, and they tend to overpredict rainfall in the peak, especially. So kind of focusing on Lake Victoria, and aside from the fact that Lake Victoria has a lot of problems with it because it's a huge body of water, there's a lot of convective storms there, so there's a lot of convective rainfall. So it's an interesting area to zoom in on. So I guess this is interesting. The GAN is kind of, I don't know, it's not really improving the diurnal cycle as much as it is over the rest of the domain, but and it tends to kind of overpredict a little bit, just like the IFS, but there is a kind of slight improvement towards the end of the day. So yeah, and I think, yeah, and continuing with that as well. So looking at something a little bit more based on, you know, a score that is more kind of based on events happening. We've been looking at things like the equitable threat score. So it's kind of looking at how well it's kind of dealing with, you know, false alarms and hit rates and false positives and stuff like that. So I'd say over the whole domain, you can kind of see that there's not really an obvious change there, like the IFS, the quantum mapped IFS in particular, after quantum mapping, tends to perform similarly with the equitable threat score. But when you look at Lake Victoria, particularly for kind of like at the higher end of rainfall, it seems like there's a reasonable improvement in the equitable threat score, not necessarily getting to the stage where the equitable threat score is like necessarily high enough for someone to say that this is a great forecast, because it's clearly coming from quite a low place already. Like, but still, that's kind of, I guess that's kind of encouraging that it's in an area where there's a lot of convective rainfall. It's managing to kind of improve some of these metrics. Oh yeah, so I have some other, I don't know how much time I've got, probably a bit. Okay, well, yeah, I think I'll just wrap up then. So yeah, we've been applying a GAN to post-process rainfall forecast in East Africa. Particularly when you compare it to a strong baseline, the main improvements are the fact that you can really correct some of the diurnal cycle. It produces realistic looking rainfall patterns, and also particularly over Lake Victoria, there seems to be some improvement in skill scores like the equitable threat score. But we do have this problem that when we get out to very, very high percentiles, there's a bit of an over prediction. So kind of thinking about how to deal with that. One thing we have been doing is, you know, quantum doing something else to the GAN output, I guess, because if you don't expect it to necessarily have good behavior in the tails, you might have to do something else to it to post-process your post-process, I suppose. But yeah, so we have been looking at like also quantum mapping some of that as well, just to kind of tame those higher percentile values. Yeah, I'll just finish there. Wait for questions.
Thank you. So any question?
So you're saying that it tends to mispredict at the high quantile ranges. As you know, weather gets more severe and we see typical weather patterns falling into these higher and higher quantile ranges, like how would you expect to improve your model to reflect like climate change effectively?
Yeah, I mean, this is always a big question with machine learning models when you're training them on a certain region, and then you try and include a temperature forcing or something and make it cope with that. And I guess the current way we've got it set up, you wouldn't really expect it to do well on data that it hasn't been trained on. And I have seen people try and get around this by feeding the model data, by rescaling the kind of input parameters in such a way to make sure that, whatever climate you feed it, you will the model will still perform well, provided you've kind of physically done something to your parameters. But yeah, one thing I should mention about those high things as well, that there is in our validation set, there is also a cyclone off the coast, which when you get to those high percentiles with this much data, you're quite swayed as well by these, by like one event, one large rainfall event can also sway this quite a lot. So one thing we are doing is going to do just assess the sampling variability we have in our validation set, just to check up to what point can you really trust these values, because otherwise it's just one event that we didn't see in our training set.
Yeah, I think I have one quick question about the zero values. So it's a zero inflated data is because you're considering rainfall. So it's a zero inflated data, right? But the GANs don't produce, output is not zero inflated. So I remember in Harris's paper, they just thresholded values. Do you treat any differently, or do you take care of that?
So you mean they had a threshold on the rainfall and just say
which ones are zero, actually? Zero values.
As in, as in they cut them off. Yeah.
So do you do that, or it's because the GAN creates a problem? It's because it doesn't produce dry days.
I don't know if I understand completely, but you're saying that it doesn't produce zero rainfall. Yeah, I guess I don't think we've noticed that being such a problem. As in, again, I guess because we've been particularly looking at these high rainfall values, not like the low rainfall values. But.
Yeah, I mean, you showed that the higher contour is a problem, but I have also seen that the GAN creates a big problem for just predicting the
zeros.
So that's because it's a zero inflated data, and it's a big problem there.
Yeah, I think spend a lot of time looking at these pictures of what the GAN does, and if you compare to the IFS, which has like a drizzle bias, it does tend to kind of take those out and produce those, like kind of make it a little bit drier. I guess it wouldn't necessarily produce an all zero, if I don't know if that's what you mean, but I haven't really seen those in the training in any of the data yet. But yeah, it does seem to do well at kind of making it a bit drier, which is one of the problems the IFS has, is it's a bit too wet at low rainfall values.
Yeah, maybe I have a related question. I'm not sure I understood what is the input of the GAN. Is it an image?
So it'll be so it's I don't know if I necessarily gave enough detail, but basically you have 20 forecast variables gridded, so 250, each forecast variable is like a picture, 250 by 250. So I have wind speeds and temperatures and things like that. So there's 20 of those, which are images, and then also orography and land sea mask, which are also also images. And so it's taking all of these into a convolutional network and performing convolutions on this big kind of cuboid of data. Does that explain?
Yeah, and so, but the image of the rainfall itself is 0, 0, 0, 0, and sometimes it rains.
The images of the rainfall, it will be like, will just be a picture where each pixel will have a value of between, of the millimeters per hour, not on and off, so millimeters per hour.
But most of the time it's 0, no?
I mean, a lot of the time it is, but we've got quite a large region and there's usually a bit of rain.
Okay, thank you.
Anything? Yeah. Hi. Did you run into any problems with kind of mode seeking behavior from the GAN, or how was the dispersion of the ensembles?
Yeah, I have some preliminary kind of results on the spread error here, which is quite a small ensemble that we're generating. I don't know if this answers your question or not, but yeah, I guess like it's not like amazingly well calibrated, but clearly. But I guess it doesn't seem like it's necessarily mode seeking. Like it's not too, I don't know, it's kind of I guess here it's kind of a mixture of under dispersed and over dispersed.
Interesting. Okay. Yeah, no, we've generally found it tended to be under dispersed, I think, but of course you can always recalibrate. Yeah,
I think I spoke to someone else in DeepMind who mentioned there was a calibration step in terms of the probability of something, but we haven't really looked into how to do that yet. So I'm interested to hear about any ideas for that.
Thanks.
Okay, well, let's thank Bobby again. So I think now is the break. I don't know yet quite how long, until 3:30. So